Welcome to my Commodore 64 Games memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have different versions of Wizball that I was able to find from the original discs. This is all thanks to Bill Johnson, who saw my earlier video and was able to send me a couple of G64 high accuracy disk images, basically, which includes all of the protection information from the original discs that were released. Here I'm running Vice side by side with the NTSC version on the left and the PAL version on the right. So here is the NTSC version on the left and the auto start disk image for G64 PAL version on the right. You can see that the NTSC version of Wizball has a different identification number in the disk, and also it has different files. So the American version is a lot different. It displays this Mindscape Presents Wizball Copyright 1987 Ocean Software screen, whereas the PAL version auto boots and quickly turns the screen off and then starts this effect while it's loading. Now I've enabled warp mode on both of the emulators, so even though they're side by side, they should be warping ahead at roughly the same speed, and the PAL Wizball version loads a lot quicker. On the NTSC version, I'm setting a breakpoint at the usual game entry address because I want that to get hit. Because actually what I want to do is that I want to save out the full memory using the monitor on both these instances of Vice. I want to save out the full memory as I was doing for the tape version. So I know that the disc version starts at the same address pretty much, so I'm just waiting now to do that on the NTSC version. I'll also do the same with the PAL version, and then we can get on to the comparison of the binary files for the full memory from 400 in hex all the way up to F0 in hex, for example, or even FFFF. Here I'm just having a quick little inspect of the auto-booted loader information that was loaded quite low down in 0 page in the beginning of the stack on the NTSC version. It just seems to load some files. We'll actually get into the differences in the NTSC and PAL versions and how they load the files in more detail later on. Here I'm just having a little quick look at the code, and it does a JSR with FFCF, and then it does some overflow checks, and then it loads X, does store into 1 to bank in the RAM underneath all of the ROMs and everything, and then stores and then banks in the ROMs and everything. It seems to be the NTSC version seems to be using the ROM loaders, the kernel ROM. So it seems to be doing a whole bunch of default stuff. It seems to be grabbing bytes individually, one at a time, from the kernel, and then storing it in the RAM underneath all of the ROMs and I/O and everything else. I would have thought that this is actually quite a slow way of doing it, and yes, I mean the NTSC version is really slow when it wants to load. You can see here that FFCF is the char in read a byte from a default input, for example, from the serial bus disk drive, basically. At this point I'm really thinking, wow, this is a very slow way of actually loading. There doesn't seem to be much in the way of a protection check as far as I can see right now in this initial look through the code. Of course, I've not gone into a great deal of detail yet with the auto booting, auto loading code from either version, so there might be a protection check hidden away somewhere, but at the moment it doesn't look like one for the NTSC version. The PAL version looks a little bit more protection checked, if you like. So for the NTSC version on the left, I've now put a breakpoint on that final jump, which looks like it's the end point where it actually tries to start running the game. Perhaps we'll see what it does in a minute once it finally finishes loading. On the right hand side, of course, you can see the title screen for the PAL version is merrily looping around and playing all by itself. So here we go. It's loaded the information as far as I can tell. Let's have a quick little disassembly of the stuff that it's loaded. It does some EOR stuff, and if I step in, you'll see that actually it looks like it's going to self-modify that branch on not equal to somewhere else. So at the moment it's branching on not equaling to somewhere which doesn't really make much sense. BDC. It's done a whole bunch of stuff here. Fairly standard default kernel loading stuff. Very boring, in fact, for the NTSC version. On the right, the PAL version is merrily going away on its looping title screen still. So today in Singapore it's National Day. If you can hear fighter aircraft running around or flying around in the sky above, and they can get quite loud, don't get worried, we're not under attack. It's just the National Day celebrations. So anyway, you can see here that the branch on not equal was self-modified. It has started descrambling the next chunk of code. The next chunk of code wants to relocate some stuff which is loaded and store it down into quite towards the end of extended 0 page, just before the first default screen, in fact. And it's doing some stuff. It's doing a few JSRs. They look a little bit suspicious. I'm going to put some breakpoints around. Well, actually, these breakpoints aren't going to get hit because actually it's going into this is code which will actually get relocated to a different part in 0 page. So what we'll do is that we will have a little look what it's really doing. Loading A with 1, PHA, PHP. So it's sending a listen. It seems to be loading some commands it wants to send from the relocated 0 page memory. So what is it, 384? 384, we can see it's doing some memory reads and some memory executes. Okay, that's cool. These are commands sent to the disk drive. So it looks like it is trying to run some code on the disk, especially with the proposed memory execute command there that you can see. So what is this code actually doing? You can see it's doing a JSR to 36A, which is the code is just copied down into the end of extended 0 page there. And it's kind of like running some extra stuff. You can see it's seeking around on the disk, and then it gets to 6389. So it seemed to be doing some checks on the drive right at the end of this really, really slow kernel load. Interesting place to do it. I suppose at the end of the game load is as good a place as any to try and execute a protection check if you really want to do it that way. I suppose, you know, it was decrypting the code by doing that EOR. So it was marginally hidden, I guess. So I guess that kind of makes sense. Anyway, so, you know, making sure that the bank is in the RAM, of course, so that we save the RAM and not ROM data. Just save it out from 400 to, you know, FFFF, usual kind of thing to do. So anyway, the NTSC version, you'll notice on the left, I mean, apart from the aspect ratio difference, there's actually, even with full debug borders on, there's a lot less vertical raster time available. Now we're going to get into more details between NTSC and PAL Commodore 64 comparisons for other games later on, but for Wizball actually it's not too different, although there are notable differences between the NTSC and PAL versions. So the NTSC version of the title screens are the same, but the game display is quite a bit different. So you'll notice actually on the NTSC version on the left hand side, the status panel for your power-ups and the colours that you've collected, it alternates across the bottom border. Only really the bottom border is opened. I mean, the top border is also opened, but the sprites aren't being displayed up in the top border. Also, you'll notice that there aren't twinkling stars in the background. The stars are static compared to the panel on the right, which has nice twinkly and parallax scrolling stars. If I move, you can see that the stars don't parallax scroll or anything else like that on the NTSC version, compared to the PAL version on the right, where if I move around on the PAL version on the right, you'll be able to see that the stars twinkle and parallax scroll. There you go, see? Nice twinkling and parallax scrolling stars. It looks a lot prettier. Here I want to have a look at how the PAL release auto boot starts. Okay, so having a look at how the PAL version auto boot loader works. It's finished loading. If we do a CPU history, we can see it goes through the vector at 326. So if something has set up 326 with the address of the code at 363. This code has been loaded by the data file. If we have a look at the memory addresses that were loaded, so we can see that there are 3 files. If we want to have a look at the files, we want to have a look at what the file contents is. And because it's a G64 file, we will use our C1541 utility to look at the contents of the G64 file that we are attempting to auto start in the emulator, and we will use this to extract the files that we can see inside the G64 file. There are the files. I can use the extract command to get the file data and to store it inside the current directory, which is what I'm going to do. Loader, F, and Wizball. So this is what loader does. It starts loading data at 0314 in hex. It then has a whole bunch of values that I would normally expect to see in the vector table, which is around about 314 in hex. And then the last address here, which is here, 0363, or that's low and high byte ordering, of course, which in hex is the start of the code which was auto booting, which then goes through the vector at 0326 in hex. There you go. Which is the kernel char out routine, which of course it uses to display ready and stuff like that. So when it wants to display status update message, instead it starts running the auto boot code. FFBA is set LFS, logical number, device number, secondary address. FFBD is setting the name, one character, F character, corresponds to the F file, which is on the disk image, loads it. FFD5, load. It's doing a load, not a verify. It's kind of like looking that it tries to load it at 400 in hex. It's actually tricking us, it's loading it at where it's been saved to. The secondary address was set, you see. It's not equal to 0, so actually it ignores the load address. And then it runs the code which was just loaded at 4000 in hex. If we have a look at the moment, M400 shows that the screen data and the data at 4000 in hex is actually just default. If we let it load, and then we do the memory checks again, there's still screen data at 400 in hex. The real code has been loaded at 4000 in hex. There we go, you see. First opcode now is 78, which is set interrupt. Okay, so we are very sure that it has ignored the request to load at a different address, and it's actually loading it the address that it wants to. So this code, it claims all of the stack and everything, but it stops the interrupts, claims all of the stack, blah blah blah. Kind of like standard startup code, to be honest. Again, it seems to be doing a whole bunch of kernel calls. However, these kernel calls are a little bit more special. So it's actually taking a whole bunch of code and it's relocating it to quite low down at the beginning of the stack. You can see there, load and store into 100 in hex, Y. It restores 330 and 331, of course, because it doesn't want to mess around with those vectors. It actually restores them back to some of the code that was just loaded. There's a little bit of code here which seems to copy the loading address to the end loaded data address at the end, which is mildly interesting. It seems to be setting up the same zero-page locations as what the normal kernel loaders would expect to update. This is making me think, and obviously I've seen how it loads, it's making me think that it's replacing the kernel load with a load of its own, which is a lot quicker. And it's just basically, it seems to be updating the same zero-page pointers just for maybe the sake of completeness or compatibility purposes later on. Just to make sure, so for example, that it seems to be a speed loader, just to make sure that the speed loader doesn't introduce incompatibilities with how the game wants to run later on, I guess. Anyway, so we're going to have a look at this code which was put in the bottom of the stack now, and we're going to see what it's doing. So there's a JSR, there's a few JSRs, quite a few JSRs in sequence down below, and then it seems to be doing increment AF, increment X. AE and AF were, if you remember, the addresses that it was expecting to update. So I think by looking at this code in a very quick glance, I can see here it's doing some loads with CIA2, which is handling the serial port, which is the port where the disk drive is being plugged into. I can see here the code at 1A0. This is really interesting. It seems to be doing, and we'll investigate it more, but it seemed on first glance, it seemed to be doing something really interesting by shifting bits from the serial port into a byte somewhere and then returning that byte value. So we can see actually it's got some disk commands in memory, initialize and also U1, which I think, if we double check, looks like block read, but we'll see. Here we are. So if I look for U1, you can see the U1 command, sub command for block read, and it gets a whole bunch of parameters for the command. I command is initialized, so it reinitializes the drive. FFE7 is clear file table. FFBD, FFBA, set name, set LFS, standard stuff. Looks like it's actually preparing to send the U1 command at this point. Doesn't open file. FFC0 is open. FFBD, set name, just to make sure. Initializes the drive first of all, of course. Set FS, open. Now, because I think it's running drive code in a short while, I actually want to check what the drive is doing. So on the left, the disassembly is the computer. On the right, the disassembly is looking at the drive. I want to double check the return when it gets the code that it's running when it gets the return from this opened stream on the serial bus, serial devices, which is the disk drive. It's running a whole bunch of verification on the returned values, and then it's running a whole bunch of extra code, and then it jumps into 100 in hex. So again, it's setting up file parameters. Again, it's trying to load data. And at this point, when it's flashing the screen on the Commodore 64 with a nice border effect, I can see now that it's running drive code in a buffer at 600 in hex in the drive's memory. This is the pointer to buffer 3, which is 600 in hex. So I know that 600 in hex is one of the internal drive buffers. Okay, so this drive code is doing interesting stuff. So this drive code, when it does a bit into the unknown here, just making sure here that the other buffer at 500 in hex in the drive doesn't really contain anything code, it just contains data which is loading, which is kind of expected. Find starter data block you see in memory, F50A. F8E0 is decode 69 GCR bytes, again, which it does some decoding inside the drive, and then these bytes are then being sent back. But this is all extra custom code which is running inside the drive now. User code, basically, the code that the game sent to it. Now this code here, now stepping through the code on the Commodore 64, the JSATA 18B in hex. What it does, if we step in, you can see here that it's looking at DD00, which is CIA 2. It's branching on plus back again until something changes. So this, I think the highest bit, which is basically 2's complement, positive or negative, either plus or minus. It also can, the lower 2 bits of CIA2 are actually also used for setting the VIC bank. Very confusing register bit layout, to be honest. Thank you, Commodore, for that. But yeah, you can see here that bit 7 is the serial bus. So yes, it's data in. So something is toggling. Sorry, here it's toggling data in, or it's waiting for data in. Then the Commodore 64 unasserts data in, which then sends back the signal to the 1541. It then was doing a whole bunch of bit shifting and then ORing into a destination register, and then that destination register was being returned, and then basically it was just doing this. Load and store into 1 to decide on whether or not to bank in or out the RAM, and then it does a store with AE indirected and with Y, and then returns, and then it does this whole cycle again while updating the file length loaded parameters. Okay, the variables. And so this is the actual transfer routine from the 1541 disk drive to the Commodore 64. It's doing a whole bunch of bit twiddling. So this first one here is that it's doing a branch on plus, so I think it was the data in line, right? So yeah, definitely, you know, plus or minus is bit 7, so data in is looking for data in, waiting for the drive to set or reset data in. It is then, after the drive has twiddled that signal, it's then storing back into there to set the signal back again from the Commodore 64. You see, 0B is 1011, so actually it's setting up the default bank 3, bank 0. It doesn't really matter what the VIC bank is because the screen is turned off, to be honest. What I'm interested in here is that it's actually twiddling ATN out. First of all, you can see load A with 0B in hex, storing it. It's twiddling ATN and then it's waiting for data in to be asserted from the drive. Once it has been asserted, it clears ATN. It then JSRs to 1D1 in hex. 1D1 in hex decrements the border and stuff like that with a bit of delay on the Commodore 64 side. This code now, if you have a look, just double checking that 1D1 does twiddle the border, which it does, it decrements it, let's see. Decrements the border, does a few knops and then returns. The Commodore 64 seems to have some knops in here. I'm guessing that this was some timing twiddling, because at this point where the Commodore 64 wants to do some loads, the drive has already been sending signals. You can see the drive disassembly on the right has already done a store into 1800 in hex, with the result of the first 2 ASLs and then the ROLs and ASLs, and then it does a store. So it looks like it's already set up the first, what looks like 2 bits. You can see here there are 4 chunks on the Commodore 64 side. There's an LDA, there's the second LDA here, right? LDA, bunch of rotate lefts, LDA, bunch of rotate lefts, LDA, rotate lefts, LDA, rotate lefts. And there's 4 of them, and it seems to be rotating out 2 bits and then storing it into A4 in hex. It does an eventual EOR and then an RTS. So this looks like it's a 2-bit transfer protocol, if you like, from the disk drive to the Commodore 64. Which, no wonder it's so fast, because actually 2-bit transfer protocols are actually nice and quick. It does do a little bit of bit twiddling for the ATN line and the data in line, just to, you know, make sure that the drive and the Commodore 64 are in sync. And it does that sync check for every byte that's loaded, but, you know, still it looks like quite an efficient 2-bit at a time transfer protocol from the 1541 to the Commodore 64. Certainly quite a good way of doing it, quite efficient, I would say. Of course, you need to really make sure that the timing between the 1541 and the Commodore 64 is precise, and that's probably why, almost certainly why actually, why the screen is disabled, because you don't want the VIC to be stealing any cycles from the Commodore 64 by disabling the screen in this way, and also obviously making sure that the sprites are off. You're not stealing cycles, so there's no unexpected gotchas. Just having a look at 1800 in hex, and you can see that it's actually the CIA output, the serial output control for the drive here, from the versatile interface adapter, the VIA. Basically the same kind of chip. ATN clock data, it has port A, port B, same as the CIA that you would normally find inside the Commodore 64. And you can see that drive code is doing that. It's doing basically the reverse and complement, if you like. It's sending out information when the C64 is looking for information, yada yada yada. The same kind of stuff. It has ATN in, ATN out, it twiddles the right bits. Commodore 64 looks for the right bits. Quite nice code. Reminds me a little bit about the code that for my drive code. When I was writing my drive code, I did include a 2-bit transfer protocol. Actually, usually it would default to 1 because I wanted to have the screen on with raster bars and sprites running around and everything else like that. So I would have a nice, steady, easy to use 1-bit protocol. where the Commodore 64 would acknowledge each bit as it was being sent from the 1541, which would cause the 1541 to then send the next bit, and so on and so forth. That meant that the Commodore 64 could be running all sorts of stuff on all sorts of interrupts and never lose bits, because it was never letting the 1541, the disk drive here, was never letting that run at full speed. It was always waiting on that to and fro protocol, that handshaking protocol. Anyway, this 2-bit protocol, I'm just double checking now the execution looks like it all works in sync. Well, you would normally expect it to, right, because it was actually loading the game code. One little thing about the Vice monitor windows for the disassembly is that they don't always update all of the cycles in the thing that you're not currently looking at. So at the moment, my device is C:, which is the Commodore. If I change the device to 8:, then it will update the disassembly for the drive, but the Commodore 64 disassembly won't be so. It won't be updated in sync. It won't show step-by-step cycle updates. The 1541, I think, if I remember rightly, actually runs a little bit faster than the Commodore 64. If I step on the Commodore 64, I should at least see at least one cycle running on the 1541, but you can see here that the disassembly is jumping ahead rather than showing a smooth progression of cycle steps. So this is the only issue that I have with this inbuilt monitor on this particular version of Vice that I'm currently using for debugging. I wish it was a little bit more finely controlled. This kind of debugging would have been almost impossible back in the old days. Of course, you are talking about having 2 separate computers linked via a serial cable. The only thing that you could really do in this circumstance is to put a logic analyzer or an oscilloscope with multi-channel, but a multi-channel logic analyzer would be better. You would put that on the serial cable, you would split it out, and then you would look at it that way. Or you would just use a lot of brain power to try and figure out what this was doing. So anyway, we let this load, and we can see that it loads all the way with this nice fast 2-bit protocol. The gap between each horizontal line that you can see should be indicating each byte that's loaded, so actually you can see that it's loading a byte actually really quite relatively quickly. We can see at 187 in hex, that final jump 6387 highlighted in red with the breakpoint, and the up above it, the other red highlighted line with the breakpoint at 16 B, is that? Yeah, the load A with D011 in hex. That's basically the start of the code after all of the loading has completed. So as I say, thank you very much, Bill Johnson, for sending these 2 original G64 disk images to me and responding to my request in the previous video. It's very interesting to note these differences between the PAL tape version and the PAL and NTSC official releases, and of course compare them to the hacked releases that were also released at the time. And we can see as it's just about to start the game code that the 1541 drive is executing stuff inside its kernel again. C14E is, if we have a look, C14E blah 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 is code which interprets the command from the computer. So basically it's saying that everything is okay. Back to the computer, no problems there, and away we go. The game will run. Do the same here, right? We save the PAL complete memory. And that's how we get to that point where we can do a comparison between the Ocean PAL tape release and the Ocean PAL disk release. And we can see all of these mostly low byte differences. So yeah, mostly low byte differences here, no real opcode differences. Apart from that, the rest of the game seems to be, roughly the same. So let's open up Beyond Compare and actually compare the binary versions though. So this is the original Ocean release tape version on the left compared to the Ocean disk PAL release on the right. So both are PAL releases, and we can start to see that there are significant differences like we were seeing with some of these hacked releases. So the official Ocean disk release are differences. The opcodes are the same, 20 is an opcode for example, but the low byte of the low and high address for the absolute JSR is different. It's 38 here and 33 in the disk PAL release. If we scroll down, we can see that a lot of these changes are low bytes of absolute addresses. So we see that these low bytes of absolute addresses, if we compare, instead of the Ocean Tape PAL release with the Ocean Disk PAL release, we compare the PAL SIR release with the PAL Disk Ocean release, we can see that actually they are identical from the start of its memory at 400 in hex all the way to the end of memory, and this last end of memory difference is just basically not really important because actually the disk version of Wizball is only loading up to FB00 in hex anyway, so these end of file differences are inconsequential. So going back to comparing the Ocean PAL tape release with the Ocean PAL disk release, we can see that these low and high addresses are subtly different, but the opcode placement within the data, within the memory, is the same. So what does that mean in real terms? Again, these look like AD is load absolute, so we can see that it's the low byte of the address which is changing there. Again here we can see that it looks like all low byte stuff. There doesn't seem to be any change with opcodes at all that I can see here. There's a few insertions and deletions, or a couple here, but the file data is still roughly in sync, apart from the low memory address. The interesting change here is actually these 5 bytes load accumulator absolute and D0, which is branch not equal, which is a 2-byte opcode, so 5 bytes in total, because the absolute address is 2 bytes, so that's 3 bytes instruction and a 2-byte instruction. These 5 bytes are in the tape PAL release, but missing from the PAL disk release. So let's have a look at the actual code, what it means in the game. So this is the PAL tape version. I'm just running it from my compressed copy because I just don't want to bother loading in the uncompressed data in the monitor. I don't want to bother typing that in. I'm letting it decompress. So let's have a look at this memory address, 6AC6, but we have to add on 400 bytes in hex to the data. So we have a look here, and we can see here that the load absolute with B872 in hex, and then the branch are not equal, which is the 2 extra opcodes that we were seeing in the tape release, and the disk release just doesn't have them. So I'm wondering what this code does. Why is it different in the tape release compared to the disk release? It seems that the added code tends to indicate bug fix. Not always, but usually. Okay, so it seems that the tape version is bug fixed compared to the disk version, which is a little bit puzzling. Again, not 100% like that all the time, but let's do a side-by-side comparison between the tape code as it's loaded and waiting to execute at 6389 compared to the disk code. So we can see, instead of looking at hex values in the memory dump, we will look at the disassembled opcodes in memory to make it a lot easier to see. Disk PAL release on the right, tape PAL release on the left, both original versions. So here we go, 6ED7, and you can see that the load A immediate with 0 and store A and PLA are actually in the tape version, but they are 2 opcodes later. It starts there, and then it goes, load, store, PLA, jump. It's there. So 6EC3 seems to be avoiding a whole bunch of code. What is at BA72 in a hex is a flag or something, right? Status flag or whatever. That you can see the rest of the code is in sync. The opcodes are in sync. It's just that the memory addresses have shifted by 3 bytes in some cases. B1D1, B1D4. The difference here is 3 bytes, but the opcodes are the same. You would expect the bytes for the addresses to change, because of course the code has shifted around all of the places where the status update variables are and stuff like that. So if we hunt in memory, let's make sure I got the bank in the RAM first. We hunt in memory for storing 8D, store absolute 8D, BA72 in hex. So we're looking for those. So let's disassemble the code at 63CF first and see what that does. We'll look a little bit before, just so that we can catch the earlier instructions. We can see here it's doing a setup, a load immediate with 0 and then storing it, BA72. Unlikely to be that. That looks more like, you know, game loop setup code rather than game loop execution code. 9E20, we can see here that it's doing a load A with EF01. Well, EF01 is all the way up in the top of memory where the graphics are in the RAM, right? Which is, you know, really quite odd. There isn't any code which executes all the way up in the top of memory. It's just, you know, sprite data. We know that from the previous videos when we were looking at the of course, it hasn't executed the game yet, so there aren't sprites there, but you know, if the game was running and we were in the level, don't forget that Wizball changes around quite a lot of the graphics as it's going between the title screen and the actual game. Because it's loading from EF01, you would expect stores to EF01 and you expect updates to the sprites. So actually, you know, the sprites are not going to be there right now. We'll just get rid of the disk version. We'll go and just run the tape version. So here we are. Let's have a look at that memory now, EF00, and we can see, oh, it's a spell bottle. So let's have a little look earlier on in the memory. These are the spell bottles that you can see in the bottom hand corner that display how much colour you've got in your cauldrons. They're not bottles, they're cauldrons. There's the first one, EE40, EE80, EEC0, EF00. These sprites get updated as you collect colours. At the moment, they seem to be empty. Of course they're empty because I haven't collected any red colour. Well, you can see actually that the graphics are quite well formatted, so that actually sprites on the Commodore 64 are 3 bytes across. That means 3 times 8, 24 pixels across, but only 21 rows tall. That is 63 bytes in total, and then the sprites are aligned on 64 byte boundaries. Anyway, so the middle of the top of the sprite is EF01, and normally that's empty. There's no color collected. So let's see what happens if we put color in the top of the sprite. So you can see that EF01 is 0. That means it's empty, transparent color, sorry, right, which shows the background, which in the border shows, you know, black. It's set up to show black because that's what the background color is. The border has been switched off, vertical border anyway. We can use different values. We can either use 10101, which is, you know, one color in the sprite, 0101 is the other color in the sprite, and 1111 is also the third color in the sprite. So we've got 3 different choices. 10, 01, or 11. Now, if we have a look at the colors that are used in the currently empty cauldron, we don't want to use 50, which is in the sprite. We don't want to use ones. I'm just looking for color combinations which don't exist. So 1C tells us that 01 and 11 exist in the sprite already, one of the grey colors. So we'll use 10, which should be, if I remember rightly, the sprite foreground color. Okay, so we'll put that in EF01 AA, which is a repeating pattern of 4 multicolored pixels for the sprite color, not the grey colors. We're just going to have a look at B800. So because it takes the sprite color and then it puts it into, what was that memory address? I forget. B8F2 or something like that, right? B872, sorry, or whatever it was. Just before there in memory, you can see it's got the congratulations bonus screen display. So I'm thinking that if we set this and then exit, the game should go, hey look, the game goes completely immediately, regardless of the color that's in the cauldron, it goes to the bonus screen. And then, you know, we move around and we can move around, we can shoot things, and it thinks that we've completed the level. the color for that level. It then goes to the Wiz screen. It allows me to select my horizontal movement. He walks across. Oh look, they filled up, but they're not draining. That's probably, and the scores are going up a lot too. So what I think is happening here is that if I set it to warp mode as well, it looks like it's not gonna complete its execution, right? I know. So what this means is that there seems to be a little bit of an inconsistency here. It's not draining the color from the cauldron, but it went into the Wiz level immediately. So this tells us that this tape version has some weird extra check. We don't quite know when it runs yet. This extra check, the tape version executes this extra check compared to the disc version, which is related to entering the bonus screen or not. Or rather, that check checks to make sure whether or not you're entering the bonus screen. Interesting. Anyway, so let's just do a quick check between the SIR release and the Ocean Disk PAL release, and of course there's no difference. So we can say that the SIR release basically took its release from the Ocean PAL disk release. Now the D64 archive release is identical, pretty much, almost 99.9%, to the Ocean Disk NTSC release. So the archive org release is basically the Ocean release just repacked. So now we know where all of these different hack release versions that I saw, we know where they come from. They come from the Ocean PAL disk and the Ocean PAL NTSC disk releases. What I am looking at now is the difference between the Ocean Disk NTSC release and the Ocean Disk tape release. Tape release is on the left, and you can see here that final difference that I was wondering about, the horizon gives immunity, right? The duplicate message or partial fragment of the message is actually there. So that confirms that the tape release and the Ocean Disk release for NTSC, it explains that difference in the message.